Big Bang. So now it is almost established that we have a model for the origin of our universe, and Big Bang model is the one which has the most evidences in its support. Like we have Earth, which is 4.5 billion light years old. We calculated its age from the radioactive dating process. So we have the Sun, which is around 5 billion light years old. The quasars, uh, the most distant and the oldest object found in the universe. These are some of the old artifacts which supports the Big Bang model. The abundance of helium in the universe through the process of nucleosynthesis. Observations of the Hubble's law and the cosmic microwave background measurements are some of the direct evidences which supports the Big Bang. And the presence of quasars, which are known to be the most distant and luminous objects of the universe, confirms that the universe has its early history. So the discovery of quasar indicates that the activity of quasar was at its peak epoch in very early state, that was around like 13 billion light years. So the latest quasar observed is in the Mars 2021. So you can see the pictures of some of the quasars. So basically the observation of quasars gives the notion that the universe appears to have an early history. So that is why its observation is the direct evidence for the Big Bang model. Next, we have the nucleosynthesis is the process through which the hydrogen and helium uh, were formed during the nuclear epoch of nuclear era and atomic epoch of matter era of the evolution of the universe, where they fuse together to form all the other existing elements of the present universe. So according to the model, uh, at certain state of the evolution, the neutrons were decayed into protons. So all the neutrons were decayed into protons. The red one are the protons and blue one are the neutrons. So this the protons into neutrons decayed much faster than the protons. So given rise to a more number of protons than neutrons. Later, these few neutrons combine with protons to form the helium atom, and the rest of the protons becomes the hydrogen atom. So you can see from the plot that the W map observation gives which is the Wilkinson microwave anisotropy probe satellite is fitting here is this line. So this gives that the hydrogen and that this is helium and hydrogen accounts for nearly all the matter in the today's universe, and the relative abundance of hydrogen is 73% by mass as compared to the helium, which is 25% by mass. So all these are consistent with the Big Bang model. Now let us talk about the most distant and the oldest things we can see. As it happens that we cannot see the moment the universe began, just because the early universe was so hot and dense that even light could not pass through it. We can think of it as a sort of fog. However, there was a moment about 380,000 years after the Big Bang when the universe was so cool enough to become clear. The temperature at which it happens is around 300 Kelvin. Everywhere, this is 3000 Kelvin. Everywhere in the universe, the temperature was identical, and this temperature it was glowing hot. So this is where the expansion of the space comes in. Since then, the universe is being expanding and cooling and even stretching a space. This moment was about to the blink of an eye, but this moment can be seen by radio antenna capable of detecting the microwaves. Why microwave, we will discuss it later. But for that reason, the oldest thing we can actually see is the cosmic microwave background radiation. So this CMB is very important and interesting part of the evidence which has several implications on the shape and age of the universe. So, so the cosmic microwave background radiation is thought to be a fainted leftover radiation from the Big Bang, or the time when the universe began that fills the universe, falling on the Earth from every direction with nearly uniform density. Uh, so as the theory goes, when the universe was born, it underwent a rapid inflation and expansion. But the universe is still expanding today, and the expansion rate appears different depending on where you are. Uh, the microwave background represents the heat left over from that Big Bang. The afterglow of the Big Bang is streaming through space. These last 14 billion years, like the heat from the sun, warm the rocks when it radiated at night. So you cannot see the microwave background with your naked eyes, but it is everywhere in the universe. It is invisible to human because it is so cold. It is so cold. Just it is 2.7 degrees above the absolute zero. This means its radiation is most visible in the microwave part of the electromagnetic spectrum. As I said, that is why it is named cosmic microwave background radiation. The discovery of the microwave background goes like this. Around 1965, two scientists, Penzias and Wilson, working with a radio telescope in Bell Labs, New Jersey, received a peculiar noise. At first, they thought that it is due to some local disturbance. So they tried to fix everything, but still there remained an annoying low-level statistic coming from all directions, all times of the day, through all the seasons. So let us go back a little. We know that when we heat any object, it starts to glow. Uh, and emit radiation with the wavelength characteristics of their temperature. So this is known as blackbody radiation. So since we know that the early universe was so hot and dense that even light could not pass through it, therefore we expect uh, the universe should radiate as a black body. So you can see that different radiation black body spectrum of the different black body radiation with different temperatures. So universe, we should expect that the universe should radiate as a black body if it is hot, and if it is radiating, then the large redshift should stretch the wavelength. And with this idea, Penzias and Wilson's realized that what they had detected was actually the cosmic microwave background, which was predicted by the Big Bang theory. We must analyze and detect these radiations of the universe with the condition that this microwave background must correspond to the radiation from a black body, which is at a temperature of nearly 3 Kelvin coming from all directions. So we know that the hot universe as it existed about 380,000 years after the Big Bang was at temperature of about 3000 Kelvin. But the shift of the spectrum of the microwave background from 3000 to 3K has to be there due to an enormous redshift, which we know as cosmological redshift. So this is what we get different from the different satellite at different times has given us from the Sky Survey. This is from the COBE in 1992, WMAP 2003, and Planck's. The latest one is 2003. COBE is the Cosmic Background Explorer. WMAP is the Wilkinson's Microwave Anisotropy Probe, and this is the Planck 2003. So you can see this is the bigger picture, the latest picture one. The fit to the cosmic background data from this COBE satellite is a perfect black body spectrum of temperature T 2.74 Kelvin. So this cosmic microwave background is a perfect black body radiation with a temperature of 3000 Kelvin. On the Earth, we see that the CMB has a black body temperature of 2.7 Kelvin. So this temperature is almost same everywhere. The temperature of the universe in the current days is 2.7 Kelvin. So that's the first big thing. But we have learned that there are very small variations in the temperature of the universe. These variations are really incredibly tiny. The hottest and coldest spots are only hundredth of a percent different from the average temperature. Our current best measurement about these variations comes from the telescope in a space called this Planck. This from this map. The astronomers using the Planck Observatory have measured the entire sky and their map of these temperature variation, which we see here. We see that the blue spots are colder than the average and the red spots are hotter. So these temperature differences are there. But do they have to do anything with the size of the universe? Let us see. It turns out uh, that these variations were caused by the sound waves in hot universe. So when the universe was very hot, so because of that sound wave, these variations are there just before it becomes transparent. And because we know that the temperature of the universe was at that time, we can measure the total amount of matter that we see in the universe. So we can also calculate the wavelength of these sound waves. The sound in the early universe is pretty much the same as the sound we hear now. So we know the fact the sound is transmitted through the variation in the density of air, and you can measure the variety of frequency. So when sound travels through a different density, there is a variation in this frequency and the corresponding wavelength. So in the early universe, due to the region of higher and the lower density, the sound wave results in hotter and colder spots in the cosmic microwave background radiations. Given that we know the wavelength of the louder sound waves in the universe before it becomes transparent, we can calculate the angular size of the most common size of hot and cold spot in this microwave background picture. Further, we can calculate what size is the most likely, and it should be 1 degree as viewed from Earth. So you must remember that it should be 1 degree as viewed from the Earth. So okay, now we are getting somewhere. So we have firm prediction of the size of hot and cold spot, which brings us closer to the question that what is the size of the universe. So now that prediction of 1 degree depend on the shape of the universe. Remember that Einstein's general theory of relativity says that the space and time can bend uh, and mold. So we have seen it. So space would be one in variety of different shapes. It is hard to imagine a space in 3 dimensions. So let us substitute this in 2-dimension analogy. So you can see that a 2D flat space is like the surface of a table. The flat means flat with zero curvature. But a 2D space could be a surface of a sphere where you kept on walking and you end up back where you started. So this is called a closed space with a positive curvature. Another possibility is the 2D space could be like a saddle or a hyperbolic. This is an example of what is called an open space and with a negative curvature. So those are the basic possibilities of the shape of the space. So how does that fit in our questions? So it comes down to the fact that light travels in a straight line in a space, but if the space is curved, then everything gets folded. So let us see the hot and cold spot of in CMB to see what I mean. So if a space is flat and if the spot in the CMB is 1 degree wide, then we get 1 degree when we measure it. This is a simple geometry that straight line travels a straight line. But that behavior does not apply everywhere. Why? Because if we suppose that the two ends start traveling on a flat space, they stay at the same fixed distance apart. But on a closed space, they will run into each other. And on an open space, they eventually diverge and get further apart. So this has consequences when measuring the apparent size of these distant spot in the microwave background radiation. So in flat space, if we get a complete triangle, but uh, the distorted triangle in case of curved space. So you can see. So you see the sum of the angles is equal to 180° when the space is flat, but it is greater than for a closed space will be greater than, and for the open space it has to be less than this. So now the telescope cannot see the whole path the light traveled. So all you see is the angle of the light coming into your eyes. So in the flat space, the angle measured to be exactly 1°, but in the closed or spherical space being greater than expected, and the angle in an open space is being smaller than the expected. So this is greater than 1° has to be, and this is less than 1°. So let us apply this to the spot of the background radiation. So we will see that the spot that are 1° in flat space will be different in curved space. So this is perfect way to test that whether the space is flat or curved. So in a flat space, the dominant size of the spot should be 1°, but in the curved or closed, the spot should look bigger. If the curve is open, the spot should look smaller. So what did Planck and other experiment find? And that the measurement found that the size of the spot is 1°. From that we conclude that the space is flat. So from this CMB which Planck have measured, and the observations, different observation and measurement, it has been found that the different spots are, when we see from the Earth, is exactly 1°. So from that we conclude that the space is flat. Or can we say it with certain? But that is an inconclusive statement. So we can say that a space appear to be flat, or measurement is consistent with the space with the curvature less than like 25.25%. So here you can see that inflation that the rapid expansion of a thing can solve the flatness problem, because a heavily curved region of the space can be made to look flat if the radius increases. You can see here. So here the curve, the space is not flat, but as the radius increases, the radius of the balloon increases, this you can see that the region is flat. The observable universe is like being look like a flat. So if the space is flat, then the universe is infinite in extent, and our visible universe is just the small bubble in the infinite sea of the universe. Similarly, if the space is like a circle or hyperbolic or open space, this is also infinite. But what if the space is like a closed shape like a sphere? So but so big that it's look flat, like the earth can look flat. So in this case, space is not infinite, it is of finite size. Now we are getting somewhere. Supposing if the universe is closed, uh, then how big it is? Then you do a careful analysis using the maximum and possible curvature allowed by the base measurement, and you find that the universe is no smaller than the 250 times bigger than the visible universe. So if this is our visible universe, and this outside this visible universe, this could be 250 times bigger than the visible universe. So we know that this from here to here, the visible universe is 92 billion light years. So this is 250 times bigger than the visible universe. So now we have the number for the age and size of the universe. So uh, the evidence that the universe began with the Big Bang is very compelling. 13.8 billion years ago, the entire universe was compressed into a microscopic singularity uh, like this that grew exponentially into the vast cosmos we see today. But what does the future holds? How will the universe end? Astronomers have been pondering the ultimate fate of the universe for thousands of years, and it is found that the fate of the universe depends on how much mass and energy is there in the universe. Okay, so it actually depends on how much mass and energy is there uh, in the universe. So, but the astronomer, what they do, they like to work mostly with the ratios. So in this case, we have the ratio of energy density over the critical density, called the density parameter, which is omega naught. So this is energy density and this is critical density. And basically omega naught is the radiation, omega due to radiation, due to matter, and due to the curvature of the space. So the critical density is going to play a very important role in deciding the fate of the universe. So three possibilities are there to the fate of the universe, and that we can look for. Uh, so critical density is defined as the density which gives us the flat universe. So that is omega naught is equal to 1. This is rho by rho naught. So the critical density is basically defined from here, the density which gives us the flat universe. That means the omega naught is equal to 1 and the universe will be flat. Okay, and has to be infinite. And finally the universe will just barely manage to expand forever because flat. And what if the density is any more than the critical density, we have the omega naught greater than 1, and then we have a close space, closed universe, and it has to be finite. In this case, the universe will eventually expand to certain extent and then it will collapse. So the universe will eventually collapse. So if the density any less than the critical density, this omega naught is less than 1, then we have open space or the saddle or hyperbolic. This situation is where the universe will be infinite, and the end will be like the universe will expand forever to the infinite time. So let us understand it with a plot between the relative size of the universe as a function of its age. So this yellow curve correspond to the rho greater than the critical density. So if the critical density was high, then there was enough mutual gravity to slow down the expansion. It will expand, and the enough mutual gravity will slow down this expansion, and within the billions of years in future, it would then collapse in on itself again. So start from here, it will expand and then it will collapse. So perhaps creating another Big Bang. So from here, then it can go again, create a Big Bang and then expand, and then so this is known as the closed universe, and the final result is known as the Big Crunch. That is that it will expand and then finally go to a black hole and singularity. So this is known as the Big Crunch. You can see the Big Crunch is expanded and then finally. Okay, the videos are not going, so it will expand and then finally it will contract, and then everything will collide with each other, the planets, all the planets, the stars, and the galaxies, and then eventually they will move towards formation of a black hole and then goes to a singularity towards where the Big Bang has started. So this is known as this is the fate. This fate is known as the big crunch of the universe. Now you can see the blue curve. Concentrate on this blue curve where the rho is less than the critical density. If the critical density was low, then there wouldn't be enough gravity to hold things together. So this case. So expansion would continue on forever and ever. Stars would die, galaxy would be, so this will be expanding forever and ever. In that expansion, ultimately what will happen that stars would die, galaxy would be separated apart, is spread apart, and everything would cool down to the background temperature of the universe. So, and this is an open universe, and the end is known as the big freeze, in which in both of the cases, if the universe is also flat, so this is also going to be when the critical density was just right, the universe expansion goes on forever. So and ultimately it slowed down, reaching a dead stop in an infinite amount of time. So this also creates a flat universe, and the end is also a big freeze. So big freeze, this is expanding, but it expanding, getting slowing down, expanding, not slowing down. But what will happen? The expansion continue forever and ever. So the star would die, galaxy would be spread apart, and everything will cool down to the background temperature, and we will see nothing. So this is a big freeze. So this is just another way to represent the fate of the universe with time. So we have Big Bang, and the universe is expanding. New galaxies are formed. In case of closed universe, it will reach a maximum expansion based on the gravitational nature. It will start to contract, and finally it was the black hole as a singularity point. But in case of open universe, it will keep on expanding forever, infinite expansion. But before moving further with certain conclusion, let us ask what is the shape of the universe? Fortunately, astronomers were able to measure the critical density of the universe using the NASA's WMAP spacecraft, and they discovered that the actual density of the universe predicts a flat universe. So that's right. So a universe is flat, and of the three choices for the universe fate, the universe is going towards the fate of a big freeze. Uh, Unfortunately, the universe had other plans and came up with a reality that nobody expected. We know that in 1998, a team of astronomers were observing distant supernova to get a sense of how fast the universe is slowing down, and they made an amazing discovery. They had found that instead of decelerating the as predicted by the critical density of the universe, the expansion of the universe is actually speeding up or accelerating. So there's some mysterious force is pushing galaxies faster and faster away from each other, accelerating an expansion of the universe. So we now call this force as the dark energy. And for the time being, astronomers have no idea what it is. All we know is that it is pushing the universe apart. So the distant galaxies are being accelerated away from us, and in trillions of years from now, they will cross beyond the cosmic horizon and disappear from the view. So the evidence that we live in a vast universe will disappear with them. So there is a strong evidence today that the universe is being dominated by the dark energy. Not only this balances the gravity, but it apparently dominates it. So if the dark energy will apparently dominates the gravity, then what will happen? What if the expansion overwhelms the gravity? Galaxy will get torn apart, and then solar system and eventually atoms themselves will be shredded by the increasing dark energy. And this idea is known as the Big Rip. So, so this is another fate of the universe. That is how the universe may end also. So this is another way to represent all the fate of the universe based on the observation of the type 1 supernovas. This is the Hubble telescope observing these supernovas. We are here in the present universe. The observation of the movement of these supernovas will decide which curve, blue, red, or pink, the universe is going to choose. The big crunch, in which the dark energy ultimately weaken over the dark matter, and the gravity will cause the universe to collapse. Or if the dark energy dominates over the dark matter, which is quite possible, then the dark energy will speed up the universe expansion, causing it to break apart suddenly, and that is the big rip. But uh, however, in the constant expansion case, the universe will keep on expanding more gradually, in balance with the gravity, and finally may leads to a big freeze, death of the universe. So still we do not know how exactly the universe will end, and all we know is theories, but it is for sure that the physics of dark energy will determine the fate of the universe. So concluding my lecture, I would list out some important points here, that the Big Bang model describes our current understanding of the universe. The universe looks like a cosmic web. It is around 13.8 billion years old, and these are the 75.3% is the dark energy, 23% is the dark matter, and only 4% of the observable universe we are looking for. So it shapes of the universe is flat. Dark matter fills the universe. It is causing the expansion, and the Hubble constant is 71 kilometer per second per megaparsec, and it is accelerating, and the responsible is the dark energy for the acceleration, and it will expand forever. So the Big Bang model, our current understanding of the universe, is a strong, it's a well-supported model. It takes into account all observed evidence, and no evidence has yet been found that contradicts it. Although it is the most complete model, but we have to explain how the universe works. There are still questions that remains for scientists and for humanity. So now we know somewhat detailed picture of how the universe behaved just moments after the Big Bang, but absolutely nothing about the moments before it. We know about the expansion of the universe and its changing nature, but still cannot predict its fate. So pushing technology to its limit, many new experiments with new generation probes and telescopes designed to study the inflation, black holes, and dark energy are coming up together, offering new evidences to further develop our model of universe. The observations from these exciting missions will continue to expand our views of space and time. Thank you.